this online lecture, we will derive the formula for the Taylor polynomial, which is often used as an approximation for a given function f around the point on the graph of f at x equals a. This is what the Taylor polynomial of degree n for f of x equals y near x equals a looks like. Since this is only an approximation, there is an error that we have to account for in order for this equation to be a true equation. This polynomial is generated around the point at x equals a, and so we will refer to x equals a as the center of the approximation. C sub 0 all the way through C sub n are constants that we will have to find. We will find these constants using integration by parts. The exception will be C sub 0, which we find by imposing the condition that the Taylor polynomial passes through the point at x equals a on the graph of f. Therefore, this error term should be 0 at x equals a. And so, plugging in a for x, each of these factors is 0, and remember, so is the error term at x equals a. And so f of a is equal to c sub 0, the only term that does not vanish when x is replaced by a in the Taylor polynomial. So we replace c sub 0 by f of a in the Taylor polynomial and get this improved version of the Taylor polynomial. We use integration by parts to find the other c sub k's, starting with c sub 1. Recall that f of x minus f of a is equal to the integral from a to x of f prime of t dt. This is simply the fundamental theorem of calculus. Note that the variable of integration, or the dummy variable, is t, not x. X is the upper limit of integration. We transform this integral, or find another form for it, using integration by parts. Our choice for u, and this might seem a little strange, is f prime of t, the obvious derivative in the integral. As a result, dv is dt. Here, all differentiation is with respect to t. And so, differentiating u with respect to t, we get du equals f double prime of t dt. As for v, from this equation, our first impulse might be to choose v equals t. But this is not the v that we will use. We take advantage of the fact that adding a constant to t, we obtain another antiderivative. That is, if we add a constant with respect to t. X is a constant with respect to t. And so, for our antiderivative, for our v, we can use t minus x. Integration by parts says that we should get uv minus the integral from a to x of v times du. U is equal to f prime of t. V is equal to t minus x. And this first part coming from integration by parts should be evaluated from a to x. And then we subtract the integral from a to x of v, which is t minus x, times du, which is f double prime dt. We plug in the limits of integration into the first term. When t is replaced by x, the product is equal to 0. When t is replaced by a, we get a minus x times f prime of a, which we subtract from 0. All we have left is to subtract this integral. But instead of simply writing out this integral to complete the last line, we will perform integration by parts on this integral. We choose u to be f double prime of t, and dv to be equal to the quantity t minus x times dt. From this, we get du equals f triple prime of t dt, and integrating this, we get v equals the square of t minus x divided by 2. And so, to complete the equation, we are subtracting u times v. U is f double prime of t, and v is the square of t minus x divided by 2. And this is evaluated from a to x. From this, we are subtracting the integral of v du. We have the square of the quantity t minus x divided by 2. Du is f triple prime dt. And we put in our closing square bracket. Simplifying this expression, the first non-zero term is f prime of a times the quantity x minus a. This expression is 0 when t is replaced by x, and so we don't write anything for it. And then we subtract the quantity when t is replaced by a, giving us f double prime of a times x minus a quantity squared all over 2 after switching all the signs. Finally, we have this integral. The viewer can guess what we're about to do. We use integration by parts again, this time for this integral. We let u be f triple prime of t, and dv will be the square of t minus x divided by 2 times dt. We leave it as an exercise for the viewer to check that du is equal to f quadruple prime of t dt, and for v we can use the cube of t minus x all over 2 times 3. So far for f of x minus f of a, we have this string of terms. And as an exercise for the viewer, carrying out integration by parts on this integral, one obtains these additional terms. One notices a recurring theme here. To add more terms to the Taylor polynomial, we use integration by parts. Applying integration by parts on this integral, the next term should be f quadruple prime at a times the fourth power of the quantity x minus a divided by 4 times 3 times 2, or 4 factorial. The general term is the nth derivative of f evaluated at a times the quantity x minus a raised to the nth power divided by n factorial. Like this expansion that involves up to the third derivative of f, and the error term involves the fourth derivative of f. The error term here will involve the n plus 1 derivative of f. Note that in addition we have this factor, the nth power of negative 1, because this integral switches signs as one goes from one integration by parts to the next. To write this error term without the integral, we use what is called the mean value theorem. The mean value theorem states that there is a value xi. Xi is a Greek letter standing in for a value between a and x, such that the error integral is equal to the n plus 1th derivative of f evaluated at xi divided by the factorial of n plus 1 times the quantity x minus a raised to the n plus 1th power. Note that there is no minus sign nor a power of minus 1 in front of this error term. And so we use this formula for this error integral. This last equation involving this long string of terms tells us precisely what the c sub k's should be. We have already seen that c sub 0 should be f of a. From the last equation, c sub 1 should be f prime of a. C sub 2 is equal to f double prime of a divided by 2. C sub 3 is f triple prime of a divided by 3 times 2. And C sub 4 is equal to f quadruple prime at a divided by 4 times 3 times 2, or 4 factorial in the denominator. In general, C sub n is equal to the nth derivative of f evaluated at a divided by n factorial. And so f of x is approximately equal to the ith derivative of f evaluated at a divided by I factorial times the quantity x minus a raised to the ith power. Here I goes from 0 through n, giving us the Taylor polynomial of degree n. Also, we regard the 0th derivative of f to be equal to f itself. Now with the error term, this becomes an equation.